Okay, now that we have extended the Fourier transform as an operator from L2 to L2, we shall look at some other properties of the Fourier transform in the same spirit. Suppose f and g are absolutely integrable functions on R. How do you define their convolution? The convolution of f and g, f star g, is a function given by f star g of x equal to integral over R f of y g of x minus y dy. It's an integral over the whole real line. It's an easy exercise for you to check that f star g is the same as g star f, and f star g is absolutely integrable. You simply integrate the absolute value of that expression for f star g and integrate it with respect to x, and you'll get a double integral and use Fibini theorem and you get the result. That's an easy exercise. I'll leave it to you to complete. There's one small comment I want to make about the convolution. The convolution integral that you see g of x minus y. And what is the meaning of x minus y in the integral? It means that the group structure of the real line plays a role in the definition of convolution. Therefore, it is essential that when you define the convolution, the domain of integration should be a group, namely in this case it is the abelian group R plus. There is one small conventional issue. If you look at books on ordinary differential equations, you will see there is a chapter on Laplace transforms and you will see convolutions described in the context of Laplace transform, and the definition is slightly different. But that definition is adapted to Laplace transforms, because when you do Laplace transforms, you are integrating over 0 to infinity. But it appears that that is not correct, because 0 to infinity is not a group, it is only a semi-group. But what exactly is happening is that when you are computing the Laplace transform, it is an integral from 0 to infinity, but really it is an integral from minus infinity to infinity, not of f but of f into h, where h is a Heaviside function. So what you do in Laplace transform is that you are given a function on the whole real line and you are clipping it off using the Heaviside function. Multiplication by Heaviside function makes it 0 on the left hand side, and then you are taking the convolution. So the definition that you see in ODE textbooks is adapted for this purpose. That is, what you see over there is not the convolution of f and g, it is a convolution of fh and gh, because the Laplace transform is basically the Laplace of f into h, where h is a Heaviside function. So I want to point out that there is no mistake, it is just a conventional matter. It is always good to emphasize the fact that the convolution involves a group structure, and I prefer it so. So now let us look at the proof of the convolution theorem. The convolution theorem says that if f and g are the Schwarz class, then the convolution is also in the Schwarz class, and the Fourier transform of the convolution is a product of the Fourier transform. That is, f convolved with g hat is f hat into g hat, equation 4.14 in the displayed slide. Now, you must recall from your ODE courses the convolution theorem for the Laplace transforms. If f and g are functions of exponential type, then the convolution of f and g, or rather the convolution of fh and gh, where h is a Heaviside function, is also of exponential type. Further, the Laplace transform of fh convolved with gh is the Laplace transform of fh into Laplace transform of gh. There is a convolution theorem for Laplace transform and there is a convolution theorem for the Fourier transform. They have the exactly same form, exactly the same structure. The transform converts the convolution into a product. If you have studied the Z transform in context of electrical engineering, that also takes the convolution into a product. So there is some method in the madness, if you will. So now let us go to the proof of the convolution theorem. First of all, there are two parts to this theorem. One is that the convolution belongs to the Schwarz class. That we shall not prove, because anyway the convolution is in L1, and all that I need for equation 4.14 is that the convolution should be in L1. And so I will work with that, and that suffices. We'll now establish the equality 4.14. Okay. So let us take the Fourier transform of f star g. What is the Fourier transform of f star g? Integral over r e to the power minus I x chi f star g x dx. What's the next step? The next step is an obvious step. You have to put in the definition of convolution, namely integral over r f of y g of x minus y dy. And the next step is again obvious. We must exchange the order of integrals. So do the x integral first. So you get integral fy dy integral over r e to the power minus I x chi g of x minus y dx. The next step is equally obvious. Put x minus y equal to z in the inner integral, namely make a change of variables, or x equal to y plus z in the innermost integral. So what do you get? F star g hat equals integral over r fy dy integral over r e to the power minus I times y plus z chi gz dz. Exponential of minus I into y plus z chi is simply a product of exponentials. E to the power minus iy chi e to the power minus iz chi. So split it, and it's a product of two integrals, f hat of chi, g hat of chi. The convolution theorem has been established. Now let us apply these things to solving partial differential equations. We have put in a lot of hard work. So now let us get some benefits, let us reap the benefits of all this hard work that we have done so far. So let's look at the heat equation. What is the heat equation? The heat equation is this equation ut minus uxx equal to 0, where I am looking at the heat equation in the upper half plane. X varies over the real line, t varies over the positive real line. So it is a half plane. The vertical axis is the time axis, the horizontal axis is the x axis, and I am looking at the heat equation for t bigger than or equal to 0. Initial heat distribution u of x comma 0 is f of x, it's given to you. Let us begin by assuming that this initial heat distribution f of x is in the Schwarz class, our favorite function space. And let us apply the Fourier transform to the heat equation, but we take the Fourier transform with respect to the x variable only and regard the t variable as a parameter. And so Fourier transform of ut will be d dt of Fourier transform of u, because everything is in the Schwarz class. It's not a problem. So we get d dt of u hat of chi t minus Fourier transform of uxx. Remember, the Fourier transform converts 1 upon I d dx into multiplication by chi. So here we got minus uxx. So when I take the Fourier transform, it will become chi squared u hat. So after taking the Fourier transform of the heat equation, we get an ODE for u hat, namely d dt of u hat plus chi squared u hat equal to 0. Okay, so you got a first order ODE, but you also need initial conditions. What is u hat of chi comma 0? U hat of chi comma 0 is f hat of chi. You simply take the initial heat distribution and take its Fourier transform. Remember, we are taking the Fourier transform with respect to the x variable. So u hat of chi comma 0 is f hat of chi. So we got a first order ODE, linear first order ODE, innocent looking object, and we got initial condition. What is the solution? U hat of chi comma t equal to constant e to the power minus t chi squared. What is the value of c? Put t equal to 0, and I know that u hat of chi comma 0 is f hat, so I got the value of c. So we get u hat of chi comma t equal to f hat of chi exponential of minus t chi squared. So we got the product on the right hand side, f hat of chi times x perf minus t chi squared. Can you write the x perf minus t chi squared as a Fourier transform of something? You can. You have to recall the formula for the Fourier transform of the Gaussian. Remember, the Fourier transform of the Gaussian is another Gaussian. So we just have to identify e to the power minus t chi squared is the Fourier transform of what? It is the Fourier transform of e to the power minus x squared by 4t. If you take e to the power minus x squared by 4t and you take the Fourier transform, you are going to get exactly e to the power minus t chi squared, except that you have to adjust the constant properly. What is the constant? 1 upon root 4 pi t. So that's exactly this function gxt. So what is gxt? Gxt equals 1 upon root 4 pi t e to the power minus x squared by 4t. This expression gxt is extremely important. It is called the heat kernel and it plays a very crucial role in many parts of mathematics such as probability theory and differential geometry, the heat kernel. So now we can write u hat of chi t as f hat of chi into g hat of chi t. But the product of two Fourier transform is the Fourier transform of the convolution, namely g star f hat. What is g star of f hat? It is an integral. It is an integral of f of s into exponential of minus x minus s the whole squared upon 4t ds with the factor 1 upon root 4 pi t thrown in, innocent constant, and that is the displayed equation on the slide, and that gives you a formula for the solution of the heat equation in the upper half plane t bigger than or equal to 0. So the formula was derived by assuming that the initial data f of x is in the Schwarz class. Now of course you will argue that the heat distribution, initial heat distribution may not be in the Schwarz class. So how do we do it? But look at the formula. The formula for the solution uxt equal to 1 upon root 4 pi t integral minus infinity to infinity f of s e to the power minus x minus s the whole squared upon 4t ds. You see the exponential factor in the integral decays to 0 very rapidly. So f need not be in the Schwarz class, it can actually grow. It can grow exponentially fast. So the function f of s can even grow exponentially fast. Never mind, the integral will still make sense and it will still satisfy the heat equation. So the formula makes sense even if f is of exponential type. So here are some examples. So let us take the heat equation with initial condition u of x comma 0 as x squared and try to solve it. So how do we solve it? We simply put f of s equal to s squared in this integral, the last displayed integral in this slide, and we have to compute this integral. And there are other examples with u of x comma 0 as cos ax, u of x comma 0 as sin ax. So please try out these examples. Now suppose we take the initial heat distribution as a continuous function which is positive on minus 1 1. So let us take a function f which is positive on minus 1 1 and 0 outside the interval minus 1 1. So outside the interval minus 1 1 the function has been defined to be 0, inside the interval minus 1 1 it is positive. So let us look at the formula. What are you integrating? You are integrating f of s. F of s is equal to 1 or say something positive, not necessarily constant. So the integral will go from minus 1 to 1. The integral will go from minus 1 to 1 and f is strictly positive, let's say, between minus 1 and 1. The exponential factor is strictly positive. So integrating a strictly positive function on minus 1 to 1, you are going to get a strictly positive function. It means that u of x comma t is going to be positive for all values of x and for all positive values of t. So look at the upper half plane. Throughout the open upper half plane, the solution is positive. The initial heat distribution was positive on minus 1 1. Now suppose you take a point which is very far away from the origin, say 1000 kilometers away from the origin, and time is very small and positive. Time is very small, say microsecond, and positive. So where is this point located? the point is located about 1,000 kilometers away from the origin and you begin the stopwatch. Time has become a few microseconds. But you see, when time was 0, at that particular point the heat distribution was 0 because f of x was 0 outside minus 1, 1 and it is positive on minus 1, 1. So this positive distribution of heat in this interval minus 1, 1 has suddenly given a positive value at a point which is 1,000 kilometers away. No matter how small positive time may be, in a few microseconds, in a few nanoseconds, doesn't matter. In other words, the heat signal has propagated instantaneously across the real line. Even a point which is very far from the origin can get the influence of heat as soon as time becomes positive. This phenomenon is expressed in physics by saying that the heat equation exhibits infinite speed of propagation. That the heat signal has propagated with infinite speed. Instantaneously, the heat becomes positive when time becomes positive, however far the point may be. How could this be possible? We cannot realize this in any physical situation. No physical process will have infinite speed of propagation. So is this a contradiction? No, it's not a contradiction. The heat equation is an approximation. It's an equation that approximates the heat distribution, the temperature distribution. True, when a point is 1,000 kilometers away from the origin, the heat has become positive, but it's very, very small, it's very negligible. E to the power minus x minus s the whole squared upon 4t. T is very small and x is very large. E to the power minus x minus s the whole squared upon 4t is going to be negligibly small. So although it has become positive, it is negligibly small. So the heat equation is nevertheless a good approximation. Despite this infinite propagation of speed, it certainly is a very good approximation.